Okay, second half of number 7, so week 7 is Taylor series. So I'm going to go over something called Taylor's formula for a function of one variable, and then just introduce a concept called big O notation. Hopefully a lot of you have seen this before, but it's a pretty simple idea just to give you an idea of how fast a function is growing or shrinking. Then I'll talk about a generalization of Taylor's formula to functions of several variables, something called Taylor series expansions, and then some applications to bond convexity. So this is just carrying on from one of the lectures from the first week where I talked about making a linear approximation to a function, and now we can add more terms to that approximation to make it a little bit better. So I'll start off with Taylor's formula for a function of one variable. So my function is going to be f of x, and I'm going to assume that it's at least n times differentiable. So when I say that, I mean I can take the derivative of f of x to get f prime, and then I can take the derivative of f prime to get f double prime, and I can continue doing that until I have n primes, and each one of those functions is going to be a differentiable function. And then I'm also going to assume that a is some real number. And a Taylor polynomial of order n around the point A is just defined to be this thing here. So what I do is I evaluate my function at the point A. So the idea is I know the value of my function at certain points, and so I'm going to pick one of those. So A is going to be that point. And then for points that are near A, I'm just going to use the derivatives to make an approximation. And basically what's going on with this polynomial, I have x minus a times the first derivative. I have x minus a squared times the second derivative divided by 2. And then I can just keep going, and the general formula is going to be x minus a to the kth power times the kth derivative evaluated at a divided by k factorial. And so that's just what the final term here is, except that the last one is n, because I said it's a Taylor polynomial of order n. So that just means I go up until I'm using x minus a to the nth power, and then that's the last term in my Taylor polynomial. And the idea of this Taylor polynomial is that I want to be able to use it to approximate f of a at points x that are near a. And so I can write this in a little bit more compact notation, just like this. So I'm going from 0 up to n. So here's the nth term on the right here, and I can think of just evaluating the function as as taking the 0th derivative. And then there's no x minus a here, because anything to the 0 power is just 1. And so I want to use p sub n to approximate f of x. And so the idea here is if I just approximated f of x by f of a, that might be reasonably close. It would just depend on how steep the function was and how far away from a I am. And then I could make my approximation a little bit better by if I know the derivative of my function at a, then I can use a linear approximation on either side of a. And then I could make it again a little bit better by adding a quadratic term. So I add a little bit of a parabola, and hopefully that'll make the approximation a bit better. And so the idea is as p sub n, as I add more terms, I'm getting a better and better approximation of f of x. But I want to be able to understand how good my approximation is. And so that's what most of today's lecture is going to be. So the questions are, does p sub n, oops, I've got this wrong, so this should be f of x, but does p sub n of x converge to n f of x as n goes to infinity? So as I add more terms, it's going to be a lot more work to calculate all these additional terms. So I want to at least know that each term I'm adding is getting me closer to what I want. And then order means how well does p sub n approximate f of x. So suppose that this actually did converge to f of x. I would still need an infinite number of terms to get exactly f of x. So I'd like to know, suppose I want to use a third order polynomial, how far away from f of x am I? So we'll measure that distance using something called approximation error. And that's just going to be defined to be the difference between f of x and p sub n of x. So p sub n of x is my polynomial that I'm using for approximation. And then f of x is the target. That's the function I'm trying to approximate. And if I measure the error using an order n Taylor polynomial, I call that the nth order Taylor approximation error. And there are two forms, there are two ways for me to get a handle on the approximation error. So the first one is called the derivative form. And so now I had to assume that f of x was at least n times differentiable in order to be able to make the Taylor polynomial that I'm using to approximate it. If I assume that I can take one more derivative than that, and that derivative is a continuous function, then there's a point C. So C is just some point in the interval between a and x. So a is the point where I've expanded my Taylor polynomial. So I'm writing my Taylor polynomial in powers of x minus a. And then x is the point where I'm trying to evaluate the function. So ideally, you want to have x pretty close to a. And then there's going to be some point C in between a and x where the following relationship holds. So I have x minus a to the n plus 1. So it sort of looks like it's the next term. But instead of evaluating the derivative at a exactly, I'm going to evaluate it at this point C that's somewhere between x and a. And and then I need to divide by the n plus 1 factorial. And that's actually not just an approximation of the error, but that's exactly equal to the error. So it depends on the choice of C. But there's some choice of C in this interval AX where the approximation error I have highlighted on the left-hand side is exactly equal to the thing on the right-hand side. And then there's also an integral form of the approximation error. So again, I need the same condition. But now I can express the Taylor approximation error. So the thing on the left-hand side is the same for both forms of the Taylor approximation error, for the derivative form and for the integral form. And now on the right-hand side, instead of having this thing that looks like the next term, it looks more like the final term in the Taylor polynomial, except it's multiplied by the n plus first derivative. And now I'm going to integrate this with respect to t from a to x. And so I've made this, I guess it kind of looks like a Taylor term, but I now, instead of having x minus a, I have x minus t. And then I'm also evaluating the n plus first derivative at the point t. But this is just a function. And then I'm just going to multiply it by this factor out in front. That'll be another function. I integrate that function with respect to t, and then use the limits a to x. And now that's going to be, again, exactly equal to the Taylor approximation error. But this has a sort of added bonus that there's not this kind of indeterminate c. So this is something you can just compute directly. But it ends up being a bit more work, because to get this form here, you've already taken n plus or n derivatives. So you just have to take one more derivative, and you're basically finished with this form up here, except that you don't know what c is. Here, you do have to still take one more derivative, but then you have potentially a complicated integral you have to evaluate to figure out what the Taylor approximation error is. So let's look at a quick example. I'm going to make a linear approximation of the function f of x equals log x around the point a equals 1. So the black curve is just log x. That's my target function. I'm going to use a first order, so p, oops, I guess I can't highlight stuff in the picture. p sub 1 of x is just a Taylor polynomial of order 1, so that's just a linear approximation. My point A was chosen because I know log of 1 is a particularly easy thing to evaluate. It's 0. So the red line touches the curve at the point x equals a, so it's 1, 0. And then you can see sort of in this interval here, maybe plus or minus a quarter from 1, it's actually a pretty good approximation of the function that I'm trying to approximate. And so this is the general form for order 1 Taylor polynomial. And then the derivative of log is just 1 over x. When I evaluate that at my point a equals 1, I just get 1. So this is my derivative, 1 over 1. My point a is 1, so I have x minus 1, that quantity to the first power. And then f of a is equal to log of 1, which is 0. So it turns out that x minus 1 is my first order Taylor polynomial to approximate log x at the point a equals 1. So now let's look at Taylor approximation error. And again, I'm going to choose another point where it's going to be easy to evaluate this. So I'm going to choose x equals e. So the log of e will just be equal to 1. So I'd log of 1 was 0. Log of e is 1. So that'll mean that I can figure out easily what the value on the left-hand side is. And let's see if we get the same thing using the integral form of the Taylor approximation error. So the definition here, I have my limits are going to be a to x, so that's 1 up to x. X minus t to the first power over 1 factorial times f. So first derivative, take the derivative of that again, so f double prime. And then I'm going to integrate that with respect to t. So I said I want to find the Taylor approximation error at the point x equals e. So the first thing I'm going to do is just replace the x's in this with e's. And now t is my variable of integration. So hopefully it should be pretty easy to see that this is just going to be, so I have minus t times negative 1 over t. That just becomes 1 over t. And then I have e times minus 1 over t squared, so that gives me minus e over t squared. And that gives me log of t plus e over t, evaluated at e and 1. And then on the left-hand side, it's pretty easy to figure out what this is. So I just end up with log of e minus e plus 1. So log of e was 1. So I get 1 plus 1 is 2, and then I still have this minus e. So I get 2 minus e. And on the right-hand side, I evaluate my integrand at the upper limit and subtract it evaluated at the lower limit. And so I end up with log of e, which is 1, plus e over e, which is another 1, minus log of 1, which is 0, plus e. So this is going to be 2, and this is going to be e. So I get 2 minus e as the approximation error on both sides. Yeah?
Why are you integrating from 1 to x? Where did that 1 come from?
So the domain of integration is a to x. Mm-hmm. And so I did my expansion around the point a equals 1. Okay. So I guess maybe up here I should have put an a. And then when I replace these with the actual values, it would be 1 to e. Because I've built an expansion at the point a, and I'm trying to evaluate how good that is at the point e. So now let's see if we can figure out the same thing using the derivative form of the Taylor approximation error. I guess one thing I wanted to point out, let's just remember that the approximation error was about 0.7. So I want to know what is the Taylor approximation error, again, at the point x equals e. So I've built a Taylor polynomial around the point a equals 1, and then I want to see how well that approximates f at the point x equals e. So this is my formula for the derivative form of the Taylor approximation error. And again, f double prime here is going to be 1 over x for the first derivative, and then minus 1 over x squared for the second derivative. So I get this minus, and then I'm evaluating it at c, so this is where the c squared came from. I have a 2 factorial, that's where this 2 came from. And then I'm interested in the point x equals e, so I'm going to replace the x with an e, so I get e minus 1 squared in the numerator. And now, because I happen to know what the true value of the Taylor approximation error is on the left-hand side, I can solve for this point c. And so what I get is that c is equal to 1.434, roughly. So these are probably irrational numbers, so they go on forever, but I've just rounded them to 3 decimal places. E is definitely an irrational number, so it has an infinite decimal representation. And so I found that c is, in fact, in between. So a was equal to 1, and then x was equal to e. So I found that the value c is in that interval. But I had to know what the Taylor approximation error was in order to be able to find that value of c. So you might ask, how is that useful? And so what we are actually able to do with this is we can't find with the derivative form the exact value of the Taylor approximation error, but you can find a bound on the Taylor approximation error. So I know that the true approximation error is going to, for this particular example, so normally this would either be ax or xa, depending on whether x is greater than a or less than a. But in this example, I know my a is equal to 1 and my x is equal to e. So I know there's some point c in between 1 and e where the true approximation error is going to occur. And then what I want to do is say, well, the absolute value of the error then must be less than or equal to the maximum value this function takes on the interval 1e. And so that's going to say, well, I don't know exactly what the Taylor approximation error is, but I can tell you that it's definitely less than whatever value I'm going to calculate on the right-hand side here. And so in this case, if I take the absolute value of the expression I had on the previous slide, I end up with e minus 1 squared divided by 2c squared. And now I want to find the value of c that's going to make this the biggest. And so it turns out this is, if I put in, so since I'm dividing by c, if I want to make this thing big, I want to make c as small as I can. But c has to be in this interval 1e. So the smallest I can make c and still stay in that interval is 1. So that tells me that the absolute value of this Taylor approximation error is less than or equal to 1/2 e minus 1 squared. And that's equal to about 1.476. So my bound on the error is roughly twice what the actual error is, because if you remember from the integral form, we were able to find it exactly, and it was about 0.7 something, the absolute value was. And so the idea here is, if this is not good enough, so if I want my approximation to be better than within 1.476 of the true value, then I need to use a more complicated polynomial to make my approximation. But I also need to know that that polynomial is actually getting closer as I add more terms. And so this lets me put a bound on the Taylor approximation error. So this is the Taylor approximation error using a first-order Taylor polynomial expanded around the point A. And this is the error at the point x equals e. And I know that I'm within 1.47 of the true value.